Hello everyone. In this video, we are going to see the explanation and implementation of a strange behavior question that came in PrepBytes Marathon October 20. Let's see the question. Arnab wrote a code, but the code is behaving strangely. He wrote a program to take a number as input and print it, but the code was printing some other number. Arnab decoded the change. If a number x is taken as input, it changes to a number y, where y is greater than x, and let count of all divisors of x and y be x1 and y1 respectively. Then x1 and 1 not equal to y1 and 1, where and is bitwise AND operator. So here we will be given a number x, and our task is to find a number y where the divisor of x, suppose if the x is equals to 2, then divisor of 2, how many divisor are there of 2? There are only two divisor of 2, that is 1 and 2 itself. So count of divisor of x and count of divisor of y, and we have to find what relation is given. How we have to find y? That x1 and y, x1 and 1, here x1 is the count of divisor of x, so x1, that is your suppose x is equal to 2, then x1 will be your 2 and 1, here and is bitwise AND 2 and 1 will should not equal to y1. Here what will be y1? Suppose I am taking y as 6 or 7, then the count of their divisor. What is the count of divisor of 6? There are 4 divisor of 6. So count of that divisor 6 to 6, count of 6 will be 4. So here 2 and 1 should be not equal to 4 and 1. The result of 2 and 1 should not equal to 4 and 1. Then we can take the value of y. But what is the catch here? That we have to find the minimum value of y. We cannot just put the randomly any value. We have to find the nearest element to x that is greater than x. Suppose it is 3. Suppose x is equal to 3. Then we have to find the next element which is greater than 3, whose count of divisor and bitwise AND 1. When we will do bitwise AND 1, it will be not equal to the count of divisor of x and its bitwise AND 1. So let's better understand this question with the help of example. Here I have also written all the important pointer that I have just told you. Let's see the example as 5. Let's see the example of 5. So how many divisors are there of 5? How many factors are there of 5? There are 1 and 5. Is there any other number that divides 5 other than 1 and 5? No. So now what we have to find? It is our x. X is equal to 5. Now what we have to find? We have to find y, which is greater than 5. So which is greater? Let's take 6. The first number which is greater than 5. Let's take it 6. So how many divisors are there of 6? There are 1, 2, 3 and 6 itself. So how many divisors? What's the count? Here the count is 2. Let's take count is equal to 2, and here count is equal to 4. So what's the result of 2 and 1? 2 and bitwise 1. So when we will do 2 and bitwise 1, as you can do in the binary 0, 1, what will be its result? Its result will be 0. And what will be its result? This is 4 in binary and this is your 1. What will be its result? Its result will be also 0. So 4 and 1 is also giving us 0. And what was the condition? That this is the condition that x1 and 1, this is, if suppose this is x1 and 1 and this is y1, here 4 is y1 and 1 should be not equal. Here they both are equal and they should be not equal to x. Okay, so this is the question. This is the explanation of the question, that what the question is asking. Like this we will check for 7, like this we will check for 8, then 9, then 10, and wherever we are getting the number, this count and bitwise AND of 1, that this is not equal to each other, there we can form a, and there we can print that number, that because that will be the minimum value of the y. So this is question asking to us. Now let's see the approach of this question. Let's build logic for this question, that how we can solve this question. Okay, for logic we have to focus more with this statement, that is x1 and 1 should be not equal to y1 and 1. Now what this statement wants to say, what we can get from this statement, that we are always ending the count with 1 only. And what will be the result if we are ending any number with 1? Either it will be 1, either it will be 1 or it will be 0, or it will be 0. There can be no other possibilities. Either it will give 1 or it will give 0. Now when will it give 1? When any number, suppose we are getting a count equals to, here I'm taking count, I'm not taking number. I'm giving you example with the help of, I'm just explaining you that when, if the count is some number, then what will be, when we will do bitwise AND with this. Okay, so we are taking, suppose we are getting a count of divisor of 9. Okay, what will be the binary of 9? Binary of 9 will be this. And what will be its bitwise AND? Its bitwise AND will be 1 with 1. Now, when we take, suppose 10, and we will do bitwise AND of it, we are getting 0. Now, when we check for, suppose we check for 7, we are getting 1. Let's check for 6. We are getting 0. Now, when will be your bitwise and 1 will be always giving 1? Then this value, that is value where 1 is present, it should be 1. So this will be only 1 in the case of odd numbers. In the case of odd numbers, when the count of divisor is odd, then it will always give you bitwise. And when you can make one important point, that when the count of divisors is odd for a number, so its result will be with bitwise and it will be always odd. So its result will be result with and 1 will be always 1. Sorry, will be always 1. And when it is even, for even number, when count of divisor is even, then result will be always 0. So now we have got this one thing, that when the count of a number is odd, then we print 1. We will get always answer as 1 with bitwise and 1. Now when the even, then count of divisor is even, we will get 0. Now we can frame this in this our mind, that when will be our count will be always odd of divisor number. When will be always, we know this pattern, we have also seen this in 8th class or 9th class when we studied the chapter of divisor, that when the count of divisor will always be odd, when the, for any number, for one number, that there it will be cases that for that number the count will be all, its divisors count will be always odd. Let's pause the video, just pause the video and think for few seconds, that focus on this system, that when the count of divisor will be always odd for any number. Okay, I think you must have thought of that, that when the number is perfect square, when the number is perfect square, its count of divisor is always odd. Always odd. Now let's check for few perfect squares. What is perfect square? Let's check for few perfect squares. It is 16. Now what is the binary of 16? Sorry, what are the factors of 16? 1, 2, 4, 8 and 16 itself. What's the total count? Count is 5. Now what's the let's take another perfect square, that is your 4. 1, 2, 4. Your count is 3. Now let's take 36. This is also perfect square. 1, 2, 3 also, and 4 also, and 8 also. Sorry, 8, not 8, 9. 9 also, 12 also, and then 18. and then 36. What's the total count? 3, 3, 6, 7, 8. We are missing anything. What we are missing? We are missing 6. We are missing 6. So 3, 3, 6, 3, 9. Total of 9 factors is there, that is odd, because 9 is 4 is dividing 36, 9 is dividing 36, 12 is dividing 36 completely, 18 is dividing, so they are factors, it's factors and total. So when you will check for every perfect square, you can check the count will be always odd. And what will be the count of divisor for rest of the numbers? Let's take a random number 11. It's prime number, so prime number will always give, either it will be divisible by 1, either it will be divisible by number itself, so it will give 2. Let's take odd number as, let's take ordinary number as 6. How many factors are there? 1, 2, 3 and 6 itself, that is 4. Let's take any ordinary number which is not perfect square, 7. What's in this case? 1 comma 7, that is 2. Let's take any ordinary number, 9. 1, 3 and 9 itself. What is your count? The count is 3. And here 9 is not ordinary number. You can see that. I thought I have taken the example with ordinary number, but here 9 is perfect square. Whose perfect square? It's the perfect square of 3. So it's giving odd number. Okay. Now let's take any ordinary number which is odd. Which is not perfect square, but which is odd. Let's take it 15. And what will be? 1, 3, 5. Is there any other number other than 15 which is dividing 15 completely? No. So there will be, count will be 4. So now you can observe the thing. Now you can easily understand from this that if we are getting, when will be your here, from here you can see that if we are getting a count of divisor as a which is odd, so we have to only get those divisor which is even. If we are getting a count of divisor for a number, if x is given, suppose x is given 4, and its number of divisor is odd, so we have to look for only integer greater than 4 whose count of divisor is even, and that will be our answer. Whose count of divisor will be even, the first number of 4 after 4 whose number of count of divisor will be even. Now when x is equal to 5, how many, what's the count is odd, so we will look for even number, that whose count is equal to even, that will be our answer. If it is odd, then even will be our answer. What's the count for 5? Count for 5 is 1 comma 5, and where it is getting divisible. Okay, sorry, by mistake I have written here odd. That's why I was thinking that why I am going wrong. It will be even. There is even count. Only 1 and 5. There are 2 count. So now we will look for odd. We will search for odd numbers. That where the divisor is or getting odd. Okay. Now we have known the approach. We have seen the approach. Now let's build the pseudo code for this. Pseudo code. What will be the pseudo code? We will firstly check the divisor. We will check the divisor. That is the, we will check the number. We will check the number. We will have number and we will check it, that is it a perfect square. If it is perfect square, if the number is perfect square, then what will be the output? The divisor will be always odd. Now we have to look for the number which is not perfect square. Look for the only number which is not perfect square. Check for number in increasing number. Check for number which is not perfect square, because this will give us, if we are getting perfect square, that means the divisors are odd. If we are checking for number which is not perfect square, that means divisor is for sure even. And if we are not getting perfect square, that means divisor is even. Then we will check for the number which is perfect square. So it will be vice versa case. First we will check if it is perfect square, then we will check for number which is not perfect square. And secondly, we will check the number which is perfect square. Then we will check for number which is not perfect square. We will check for the number which is perfect square. So this was the algorithm, you can say, not pseudocode. This was the algorithm. I will also show you the implementation of this code. Let's see the next. This was the approach. I hope you have understood this approach. Now let's see the implementation of this question. Okay, so now we will see the implementation of this question. Let's see the implementation. The Here I have just taken the input, that is your test case, and only one single input of integer type, that is your x. And then after x, I'm just checking in this count divisor function whether whether it is the function, the number is perfect square or not. How I'm checking? I'm just doing the square root of that. Suppose if the number is 16, the square root of it will be 4, and 4 into 4 we will get back the number that is equal to 16. Then we will return true, else we will return false. And then we will and we are storing in this currently in f the value of the whether it is true or whether it is false. We are storing it in this f variable, boolean f variable. Suppose it is odd, suppose it is a perfect number, so it will be true. Now we will be looking, if it is true, then what is the meaning of it? That it will be having odd number of divisor. Now what we want the number which is even number, which has even divisors, count of devices whose is even. Now, for looking even number of devices, the number should not be a perfect number. So again, we will check. We start looping from I is equal to n plus 1. And we will keep initially g is equal to true. And while it is true, we will keep on checking it. Is the next number. Suppose we are getting 16 and it's a perfect number. And so it's odd divisor. We will now check for the number which is not odd divisor, which do not have odd divisor, which has even divisor. So it will be always a perfect number. So we will keep on checking in this count divisor. We will first pass 17, then 18, then 19, then 20. And initially at the point, if we getting false here, that the number is not divisor, not perfect number, not perfect square. So we will just print that number. We will just, and we will make this g will be false, and this loop will be breaking. This loop will be discontinued and it will jump out of the loop. And in else, just we are doing the vice versa condition. So this was all about the implementation of the question. Hope you have been able to understand the implementation as well as the explanation. In this question, nothing we have to see is only that the number is perfect square or not, and according to that we have to perform our implementation. There was nothing else in this question. Okay, thank you for watching.